Okay, everyone, I think we're ready to start. Welcome to those who made it. It's not many of you. So the first talk it shouldn't show up here, okay. The first talk will be by Arushi Goel, who will present joint work with Matthias Hall Andersen, Gabriel Kapchuk, and Nicolas Spooner. And the title of the talk is Speed Stacking Fast Sublinear Zero Knowledge Proofs for Disjunctions. So, please.
Thanks for the introduction. Hi, everyone. I'm going to talk about this work on designing efficient sublinear proofs for disjunctions. And as Carla mentioned, this is joint work with Matthias, Gabe, and Nick. Okay, so we've all seen several talks on zero knowledge at Eurocrypt, so I'm going to take the liberty of assuming that everyone is already familiar with the notion of zero knowledge proofs and keep this introduction super short. So zero knowledge proofs allow a prover to convince a verifier that some statement X belongs in an NP language via an interactive protocol. The security guaranteed by such proof systems is that a cheating prover cannot convince the verifier if the statement does not belong in the language, and the verifier should not learn anything about the secret witness that the prover used to prove membership of the statement in the NP language. We have several types of zero knowledge proof systems now, but in this talk I'm going to focus on a specific class called public coin interactive zero knowledge proofs. These are protocols where the verifier's messages are simply his random coins. We are going to assume that the verifier is semi-honest, and it's well known that such protocols can be made non-interactive in the random oracle model. Also in this work, we are interested in sublinear public coin zero knowledge proofs, where the proof size and sometimes also the verifier time is sublinear in the size of the computation that the prover is trying to give a proof about. Okay, so as the title of this talk suggested, we are interested in designing zero knowledge proofs for a special subclass of NP languages, namely ones that admit disjunctive statements. These are statements of the following form. So let's say we have a set of statements and their associated NP languages, and the prover wants to prove that at least one of these statements belongs in the corresponding NP language. But before discussing what we achieve in our work, let me first sort of address the question about why we care about disjunctions. So it turns out that disjunctions are a pretty interesting class of NP languages that show up quite naturally in several applications. For example, they're used in ring signatures, which are now extensively used in confidential transactions on blockchains, or for example, when proving existence of bugs in code without actually revealing what the bug is. Also for verifying authenticity of images displayed in the media to combat disinformation without violating privacy of any sensitive information that might have been edited out of these images. Okay, so as a result of this, it's not surprising that while it's possible to prove such statements using any generic zero knowledge proof system that works for NP complete languages, there is a significant amount of research that has been dedicated towards leveraging the unique structure of these languages to design specialized and more efficient protocols for disjunctions. And this list here that I've displayed is by no means an exhaustive list. In this work, the main question that we are trying to address is whether it's possible to design a general framework for efficiently composing sublinear zero knowledge proofs for disjunctions. And when I say sublinear zero knowledge proofs, I'm only talking about public coin interactive proofs here. But this question is still a little vague. To begin with, what do I mean by efficient here? So the proof size in sublinear proof systems is already pretty small. So what we want to do is to somehow ensure that the prover runtime is also sublinear when computing a proof for disjunctions. Indeed, if we naively use existing protocols to compute a proof about disjunctions, the prover time depends on the size of all the clauses in the disjunction. We want to try and do something better. Now let me explain what I mean by efficiently composing here. Let's say we start with the following statements and their associated NP languages. And let's also assume that we already have some interactive zero-knowledge proofs that can be used to prove membership of these statements in the respective language. I'm going to denote the proofs generated in these protocols using these colorful cups. And I'm hoping this will start making sense in a minute. So given this, what I want to do is to somehow combine these existing proof systems so that for these individual, okay, that didn't work. Okay, anyhow. Okay, so I want to somehow combine these existing protocols for the individual languages into a new protocol so that that can be used to prove a disjunction of these statements. Classical results by Kramer et al. And Abe et al. Gave us a way to do this for Sigma protocols, which are essentially 3-round zero-knowledge interactive proof systems. And the resulting proof in these compilers is just a concatenation of the proofs for the individual clauses. Therefore, the size of the resulting proof in these compiled protocols that they designed was proportional to the size of all the proofs for all the clauses. Recently, in a prior work, we improved upon this and proposed a more efficient composition framework for Sigma protocols, which we called stacking, where the size of the resulting proof only depends on the size of one of the clauses. However, the prover computation time in the resulting stacked proof in this prior work still depends linearly on the size of all of the clauses. Therefore, in this work, what we ask is whether the stacking framework can somehow be extended to multi-round sublinear public coin proof systems, and if it's possible to also get speed up during the stacking process, so that we can get sublinear sized proofs for disjunctions that have sublinear prover runtimes. Okay, so formally speaking, our results are as follows. We extend the stacking framework developed in our prior work to also work with multi-round interactive zero-knowledge proof systems. We show that several existing sublinear proof systems are compatible with this framework, and the proof size in the resulting stacked protocol depends linearly on the proof size for one of the clauses, plus it depends logarithmically in the total number of clauses in the disjunction. We additionally notice that the prover runtime in this framework depends on the time required to generate the proof for a single clause, plus the time required to generate a simulated transcript for the remaining clauses. We also additionally observe that that in sublinear proof systems, often the time to generate a simulated transcript is much shorter than the time to generate an honest proof. And the simple observation allows us to then demonstrate that it is indeed possible to get sublinear runtimes when stacking sublinear sized proofs for disjunctions. Okay, so now before I talk about the techniques that we develop in this work, let me quickly recall how the previous work was stacking Sigma protocols. Let's say we already have these existing Sigma protocols that can be used to give a proof about these individual statements. In this example, I'm going to assume that the prover has a witness for the second clause. Okay, so to compose the proofs for disjunctions, one simple modification that can be made is to simply reuse the verifier's message. And since this is statement independent, we can easily reuse them. Also, since the prover already has a witness for the second clause, it can honestly compute the transcript corresponding to the second clause. But what about the remaining messages? The prover does not have a witness corresponding to the first and the third clause here. How does it compute the messages corresponding to these statements? So to resolve this, the Stacking Sigma's paper made two observations about Sigma protocols. The first observation was that the simulation strategy in most existing Sigma protocols works as follows. So we start by sampling a random verifier's challenge message, then compute the corresponding third round message, and then given these two messages along with the statement, the first round message can actually be computed deterministically. The second observation that they made was that, again, in several existing Sigma protocols, given a challenge, the third round messages are similarly distributed across all statements. Okay, so now going back to how such Sigma protocols can be stacked. Again, since the prover cannot compute A1 and A3 here, since it does not have the witnesses corresponding to these clauses, instead what the prover is going to do is send a vector commitment in the first round. So this vector commitment includes the honestly computed message corresponding to the first round message of the second clause, and it's going to put some garbage placeholder values for the remaining clauses for which it does not have the witness. It then receives some challenge message from the verifier, and now given these two, it first honestly computes the third round message for the second clause, then simulates the first round messages for the inactive clauses. Note here that it's using the second round message for the third round message for the active clause to simulate messages for all of the branches. It then equivocates the commitment to a new vector where the placeholder garbage values are replaced with these newly simulated first round messages for the inactive clauses. It then sends this third round message along with the equivocated opening. The verifier's work is simple here. The verifier simply recomputes the first round messages for all clauses. It checks if these messages are consistent with the commitment and opening that it received from the prover, and then checks if all of the three transcripts satisfy. And notice here that the verifier is using the same third round message to verify all three transcripts. Okay, so clearly this protocol here requires some special properties from the commitment scheme that was used in the first place. And the Stacking Sigma's paper introduced this notion of partially binding vector commitments, where 1 out of the n positions are binding, while the rest can be equivocated by the sender. And this binding position must be fixed at the time of commitment and can be chosen by the sender. But for the sake of zero knowledge, it's ensured that this binding position remains hidden from the receiver. Okay, so that concludes the summary of what this prior work was doing. The communication complexity for the resulting protocol here is easy to see. It depends on the proof size for computing a single branch plus the size of the commitment, which can be super short, potentially even just dependent on the security parameter, plus the size of opening, which would be linear in the number of clauses here, but it can be made logarithmic using a simple recursion technique. Okay, so now let's get to how we extend these ideas to multi-round proof systems in this work, and how when stacking sublinear proofs, it is indeed possible to get sublinear computation time. Okay, so when we discussed stacking Sigma protocols, we basically talked about dividing the messages sent by the prover into two types. One type was recyclable or reusable across all clauses, while the second one was deterministically computable given the remaining transcript. Now, if I want to extend these ideas to the multi-round zero-knowledge interactive proof setting, the question is, how do we get a similar division of messages in this multi-round setting? And clearly, there are multiple ways to divide messages here. But for the sake of generality, we are going to adopt the following approach. We essentially say that the messages sent by the prover in every round could potentially be divided into ones that are recyclable or reusable across all clauses, and ones that can be computed deterministically given the statement and all of the remaining messages. Now, to stack such multi-round interactive proofs, we use a similar strategy as before. So again, let's assume that the prover has the witness corresponding to the second clause here. And now again, as before, since it has the witness for the second clause, it can compute the messages corresponding to the transcript for this clause honestly. For the remaining messages that it cannot compute honestly, it's going to do the following. So it's going to send the honestly computed recyclable message for the second clause in the clear. For the remaining deterministically computable messages, it's going to create another partially binding vector commitment. Where again, as before, we use some garbage values as placeholders for the inactive clauses. It then, let's say, receives a message from the verifier. In the third round, it's going to adopt the exact same strategy. Again, send the recyclable message in the clear and create a partially binding commitment for the deterministically computable messages. And the same strategy continues up until the last round. Just before the last round, it computes the recyclable message for the active clause. It then simulates all the remaining deterministic messages for the inactive clauses, and then equivocates all of the commitments that were sent in this interactive protocol. It sends these messages and the openings, and the verifier checks are again as before. The verifier simulates or computes all the deterministically computable messages for all clauses himself, and then checks if they are consistent with the commitments and openings sent by the prover. Okay, so the communication complexity here is almost identical to what it was in the stacking sigmas case, except that now if we are assuming that we started with a k-round protocol, we send order of k commitments. So our proof size, the proof size is k times the number of commitments that we want to send, plus the size of openings, plus the proof size for proving one of the branches. And the computation time here, if you note, depends on the time to prove a single branch or generate the messages corresponding to a single branch honestly, plus the time to simulate messages for the remaining branches. And if the time to simulate deterministically computable messages here is less than the time to compute these messages honestly, we will get sublinear computation times. Okay, so beyond extending this compiler to the interactive setting, our main or the bulk of our contribution lies in sort of applying this compiler to two classes of sublinear proof systems. The first type that we consider are those based on folding arguments, and the other one is based on interactive oracle proofs. And we get varying computational savings in each of these protocols. This is essentially because of varying simulation times in these protocols. If we think about it, the job of the simulator in a zero-knowledge proof is to essentially fool the verifier in some sense, which is why it's often the case that the work of the simulator is somewhat proportional to the work done by the verifier. And here, for instance, we see that when we try to adapt bullet proofs or stack bullet proofs in compressed sigma protocols, since these protocols have sublinear size, but the verifier or the verification time is linear, we don't get any asymptotic savings. But in the case of compressed sigma protocols, we do get some concrete savings for the case of disjunctions. And this is also almost the case with Aurora, which also has linear verification time. But for the case of Fractal, we show that it can be slightly tweaked to get significant asymptotic savings, where the prover runtime for the resulting protocol only depends on the time to generate a proof for one of the clauses, plus linearly in the number of clauses. To conclude, we extend the stacking framework to multi-round zero-knowledge interactive proofs and show that several existing sublinear proof systems are compatible with this framework. The proof size that we achieve is similar to the case of stacking sigmas, although proof size in sublinear proof systems is not a big deal in any case. Our main contribution is in reducing the prover runtime, where we show that the prover runtime here only depends on the prover time for a single branch, plus the time to simulate the remaining branches, which allows us to get significant savings when stacking sublinear proofs.
Okay.
Thanks.
Thank you. Thank you for the great talk. So any questions from the audience? Are you going to ask a question? Okay, so please go ahead.
You can go ahead. Thanks for the talk. Great slides. So my question is, did you consider using your protocol to prove or argue about the correctness of machine computations? And if so, where are the difficulties?
Sorry, what do you mean by machine? Like RAM programs?
Yeah, so in a machine computation, you have a set of instructions, and in each step, you just want to prove the correctness of one instead of all of them.
Right.
And so could this
So
be...
I believe we can, I mean, this would just be an application of disjunctions, and we can use our protocol. Here we were just focusing on designing a general protocol, but you should be able to get computational savings when using it in that application.
Okay, interesting. Thanks.
I was wondering whether if the starting zero-knowledge IP is an argument of knowledge, whether the compiled protocol is still an argument of knowledge. So do you retain knowledge extraction or not?
So I believe we can argue argument of knowledge if the underlying protocol is, but in the paper we just wanted to keep the proof simple, so we did not argue argument of knowledge. Okay. But I don't see any immediate barriers in proving that.
Okay, thank you.
Thank you for your talk. In the Eurocrypt 2022 paper, there was a construction on, based on Ligero also and KKW. If you could elaborate your results with those ones instead of just the Sigma protocols that you had last year.
I'm sorry, can you repeat the question?
No, so you compared now your new results with your results about stacking last year on Sigma protocols, but you also had the results about stacking Ligero and KKW. So if you can compare your new results with those ones. KKW and Ligero.
And KKW, yeah, those were in the Stacking Sigma's paper. That was just trying to show that KKW and Ligero are amenable to stacking or are compatible with the stacking framework.
Yeah, they were multi-round already and with some succinctness also, right?
So yes, so there what we did, because we didn't care about prover computation time, we sort of were cheating a little bit and considered, so for example, Ligero is a 5-round interactive protocol. What we did was we viewed it as a 3-round Sigma protocol in the random oracle model and then applied the compiler there, which gave us communication savings. But using this framework, you can also just directly apply it to the 5-round version as opposed to...
Thank you very much.
Okay, we have to move on because, okay, thank you, Arush. Benedict? Okay, so next talk is Hyperplunk, Plunk with linear time prover and high degree custom gates by Binary Chain, Benedict Boons, Dan Bonnet, and Senfei Zhang. And Benedict will give the talk, so.
Okay, yeah, thank you. Binny was supposed to give the talk, but unfortunately due to visa issues, he wasn't able to attend. So you have to deal with me for this. But I'm excited to tell you today about Hyperplunk. And Hyperplunk is a zero-knowledge, succinct, non-interactive argument of knowledge, or it allows us to build such things, where we have a ZK snark. In general, we have a circuit that we want to prove some sort of statement on, and particularly we want to prove that given some public inputs, called the instance, I know a private witness such that the circuit is satisfied. And importantly, there is a setup algorithm here which creates a proving key that the prover has access to and a verification key that the verifier uses. And these zero-knowledge proofs have several properties. We likely want them to be knowledge-sound. We just heard a lot about zero-knowledge. But also there's 2 additional efficiency properties that we might care about. One of them being that the proofs are short, they're succinct, and additionally that they're fast to verify. And this last point here is something that is of particular focus for this talk. And it's of particular focus, especially for some certain applications. So one of these applications is something called a rollup. So today, if you look at most blockchains, the way it works is that every user creates some transactions, broadcasts them to all the miners or validators, and every single miner or validator has to verify every single transaction. The idea of a rollup is that we put something in the middle here, namely a rollup server, that collects a set of transactions, verifies all of them, and then produces a short proof, pi, that all of these transactions are valid, and then posts to the blockchain a summary transaction and additionally this proof pi. And now all the miners only have to verify this proof pi in order to be convinced that all of the original transactions were valid. And ideally, these systems make sense if verifying this proof or the snark is significantly easier than verifying all the individual transactions. So if we want to design such a rollup for, say, a system like Ethereum, where you have complex smart contracts, then we really need several properties of our proof system in order for this to make sense. So ideally, we need, these are very large statements, especially if we want to make statements about the entire Ethereum virtual machine. So we need a fast prover for these large statements, because otherwise the overhead of creating this rollup proof is going to be too large. Additionally, we need a small proof size and efficient verification, because these proofs are going to be checked within a smart contract, and these smart contracts have significantly less computational power than the prover who might create the proof. And finally, it's significantly easier to design these proofs if we have a powerful circuit constraint system that allows us to express things, core components of a smart contract or core components of this virtual machine. Additionally, a new criterion that has become more in focus over the recent year is so-called hardware friendliness. So people are thinking about designing custom hardware for these proof systems. So, for example, an ASIC or an FPGA. And in order to make this process easier and cheaper and have better bang for your buck, you want the proof system to be highly parallelizable and ideally have low memory overhead, because this it makes it easier to design hardware for these things. So if we take a look at what modern snarks look like, they're usually, a lot of them follow a similar recipe. So they start with something called a poly-IOP. And in a poly-IOP, this is an information theoretic protocol where the prover sends polynomials to the verifier, and the verifier can verify the statement by simply evaluating the polynomial at a couple points. It can also send back challenges, but it then evaluates the polynomials at a couple points and uses these evaluations to verify the prover's claims. This is an information theoretic proof system, but it's not efficient because it requires the prover to send these oracles to polynomials, which don't exist, or if you send the entire polynomial, this certainly wouldn't be efficient. So we combine this with something called a polynomial commitment, where the prover will commit to the polynomial in usually a compressing commitment, so this is short, and then give a specialized snark for the evaluation statement. So it claims that the evaluation of the polynomial at a point has some value, and then proves that this step is correct. And this nicely breaks apart these two steps, and fortunately we have a theorem that says that a poly-IOP for a circuit plus a polynomial commitment gives you a snark for a circuit, and the properties of the snark are essentially the sum of the properties of these two components. So what we design is a new poly-IOP, the Hyperplunk or Hyperplunk Plus poly-IOP, which has a couple attractive properties. The first one and most important one is that it has a linear time prover, and in particular that it does not require the use of fast Fourier transforms, which also necessitate using certain kinds of fields. Additionally, it also has expressive gate support, small proof size, it's hardware optimization friendly, and it's the first linear time snark that has all of these properties. This high degree gate support that we focus on is basically saying that I cannot just do additions and multiplications in my circuit, but I can have more expressive gates, and we'll talk about that a little bit later. And it's Plunk already, which is what we're based on, already has some level of high degree support, but it turns out that in Hyperplunk, you can have higher degree, you can support higher degree gates. Additionally, we support so-called lookup gates. Lookup gates allow you to prove that some value is in some pre-computed table or some online computed table. And this has a lot of applications, and it's the first linear time poly-IOP that supports this. And also, so this is all on the poly-IOP part. We also do some work on the polynomial commitment part. So we introduce the Orion Plus polynomial commitment scheme, which is an improvement on some of these state-of-the-art linear time polynomial commitment schemes. And we significantly reduce the proof size from 5 megabytes to something that is less than 10 kilobytes. And Hyperplunk is already actively being developed in industry, and there's certainly significant interest for using this for these EVM rollups. So I want to start with an overview of how Plunk, the Plunk poly IOP works. So at a very high level, I'm going to start with some circuit here, some arithmetic circuit over some finite field with addition and multiplication gates. And the first step in Plunk is to interpolate 3 polynomials, one for each input and one for the output, such that L of I is the left input of the ith gate. And then once I have these polynomials, I can define a so-called circuit check. So the circuit check for all addition gates simply checks that the left input plus the right input is equal to the output for those gates, and for the multiplication, well, it checks the multiplication. Additionally, I need to define what an addition and a multiplication gate is. So I will have a so-called selector polynomial, which is 1 if it's an addition gate and 0 if it's a multiplication gate. This selector polynomial simply defines the circuit, so we can usually pre-process this polynomial. So now I can write one unified equation, which says that selector times the addition plus 1 minus selector times the multiplication is equal to the output, and this has to hold true for all gates. And if this holds true for all gates, so what does the selector do? Well, if the selector is 1, then we have the addition gate, and if the selector is 0, then we have the multiplication gates. But if this holds over all gates, then we know that all of the constraints in the circuit are satisfied. I want to go back a little bit to this first step of saying that we need to encode these polynomials. So we need to find polynomials such that at I, and actually what we do is we define these roots of unity in Plunk, such that L of the first root of unity is equal to the first left input of the first gate, and so on and so forth. So we do this and find these polynomials that agree with these with our computation trace here. But interpolating, how do I do this actually efficiently? Well, interpolating these polynomials requires the use, or is only efficient, even somewhat efficient, if we use a fast Fourier transform, or also a number theoretic transform. And this runs in time n log n. So if I have n gates, or if my polynomial is of degree n, then this runs in time n log n. And also, to even achieve this subquadratic runtime, I need, ideally I need an FFT-friendly field. So I need a large root of unity in this field. And also there's a linear number of complex memory accesses, and that makes it hard to parallelize this process. And this is maybe not a problem for small n, because then other factors in the proof system tend to dominate. But once you get to very large n, like maybe significantly over 1 million, then this becomes actually the bottleneck. These FFTs tend to become the bottleneck. I also need to do many of them. And the other issue is that this becomes a bottleneck the more parallel my implementation is, so especially for hardware implementations. So we try to resolve this and get rid of this FFT, and the first idea is something that has been done before, is to not use univariate polynomials, but instead use multilinear functions. So we're not going to encode our polynomial over these roots of unity, but instead we're going to encode things over the Boolean hypercube. So simply the value is 0, 0, 0, 0, 1 over the Boolean hypercube, and we'll find these multilinear functions. So these are functions with log n variables, and they're linear in each one. And the benefit of this is that now the process of interpolation is linear time and highly parallelizable. This idea has been used before, but for our R1CS circuit. And in the end, we need to show, again, right, we need to show that our gate constraint is satisfied. And in order to do that, we leverage the classic sum check protocol, which is an interactive round protocol which has mu rounds and O of mu verifier time. So mu again is equal to log n. I told you about these, how to show that all of these gates are satisfied, but I actually omitted one step. There's one additional thing that I need to convince you of, which is I need to show that the wiring in this circuit is correct. So if you notice here, there's a bunch of values that are the same. Well, this is because the output of gate 1 is equal to the right input of gate 2. So we can map this out here. All the values with the same colors have to be the same. So how do I prove this? Well, what I do is I write down all of my entire computation trace, and then I have to show to you that there exists that there is a fixed permutation pi such that LR of O is equal to the permutation applied to LR of O. And this is called the permutation check, and it shows that the wiring of the circuit is correct. And we developed 2 new permutation checks, now using our multilinear polynomials. One of them reduces things to a so-called multiset check. I'd show that f, which is equal to these values LR and O, comma I is equal to, or the set of fi, comma I is equal to the set of fi, comma pi I, so the permutation of I. And if those sets are the same, then this implies that the permutation check is correct. You can reduce this to, we reduce this down to a couple other tools. And the advantage of this approach is that it has linear prover time. There's one disadvantage of this check, which is because of this product check here, we have a soundness error that is the size of H, so the size of the set that I'm doing the permutation for, over the size of the field. So this is not an issue if my field is exponentially large, like it's a 256-bit field and H might be on the order of, say, 2 to the 30, then this is not an issue. But it is an issue if I want to use small fields. And the advantage of using small fields is that they might be significantly more efficient. So we develop a second permutation check, and this relies on a zero check, so showing that f of x minus f of pi of x, where pi is a multilinear polynomial again, or pi tilde, is equal to 0 on all the values in H. The issue is, if we do this naively, then this is actually not a multilinear polynomial anymore. This is a multi-quadratic polynomial here, and so naively has a quadratic prover runtime. However, we can take advantage of the fact that pi tilde here is not some arbitrary polynomial, but it is a permutation, so it has significant structure, and this allows us to get, again, quasi-linear prover time. So the second protocol now has significantly better soundness error. The soundness error is only proportional to log squared of H, so log squared of the size of the set, so also works for significantly smaller fields. The trade-off, however, is that our prover time now has increased from linear to quasi-linear. So it's a very interesting open problem. If we can get something with soundness error here on the right and with fully linear prover time. But that's an open problem. So here are the, we broke Hyperplunk down into these 2 components, the gate check and the permutation check. And all of these rely on a subset of other small tools. So we really try to break down the protocol to make it, make this slide maybe harder to read, but the protocol hopefully easier to read. And all of them avoids the use of FFTs using multilinear polynomials and the Boolean hypercube. I want to talk about maybe 1 or 2 more things, which is the use of high-degree gates. So in the beginning, I told you about how to do addition and multiplication gates, but this approach is actually not just limited to additions and multiplications, but I can insert some kind of arbitrary gate function here. And in fact, I can have, so this can be a high-degree gate, so for example, Ly to the power of 5 times R of y. And the gate formula can be more general. It can have more terms and different selectors, so I don't even just need 2 selectors. So the benefit of using these high-degree gates is that if I have more expressive gates, I maybe need less wires or need less of the gates, so it can reduce the size of the circuit and the witness, so this becomes a faster prover, and this is especially true if I have operations like an elliptic curve addition, which is a cubic gate, or some of these more modern hash functions become much more efficient if I have more expressive gates. So Plonk already has support for these higher degree gates, but at the core of Plonk is this so-called quotient check, where I show that a polynomial is 0 on H by showing that it is divisible by the 0 polynomial on H. And this quotient polynomial has a degree which is proportional to the degree of the highest gate. So if I increase the degree of the highest gate, well, then it means as part of the protocol, I need to commit to Q of X. So the higher the grade, the degree becomes, the more expensive it becomes to commit to this quotient polynomial. So in practice, this means that I can probably only support degrees up to maybe 5 or 8. For us, however, the Hyperplunk only allows us, I'll have 2 more slides. So Hyperplunk allows us to use high degree gates without increasing the number of group operations. It only increases the number of field operations, so we can support much higher degree gates. I'll skip over these lookup gates, which allow us to these lookup gates allow us to check that something is in a range. The one last thing, the last 2 things that we do in the paper is that we batch all of these polynomial evaluations. So we give a new protocol for batching all these multivariate polynomial evaluations, which has significant practical implications. And we show that our protocol is a lot faster than both Plonk and also Spartan, which are 2 previous protocols. So, yep, thank you very much.
Okay, thank you. Thank you very much for the great talk. Any questions? Run.
Hey, Benedict, thank you very much for your talk. One of the goals you mentioned at the beginning was zero knowledge. So I was wondering whether your lookup gate, your permutation argument, and your polynomial evaluation at the very end, because at the very end of some check, you need to do some polynomial evaluation protocol. So are those zero knowledge, or did you gloss over that?
Yeah, we actually give there's there's been previous work on fairly general compilers where you can show that how to transform all of these things into zero knowledge protocols. So
efficiency though then?
No, it really has fairly reduced, like the efficiency cost is not very high. You essentially just need to increase the degree, or for us, the number of variables by 1, or by the number of points that the polynomial is being evaluated on.
So if you're talking about your polynomial evaluation, like you had the PCS at the very end.
Yes, so the PCS is going to be hiding. So it hides the polynomial that is being committed to, and the evaluation is going to be zero knowledge. And you can then ensure that if you query only outside of H, and you've added some randomness to your polynomial, then you can, there's general compilers that we also talk about in the paper that make the resulting snark zero knowledge.
Okay, thank you very much.
But yeah, good question.
May I add one question? Mm-hmm. So one thing is that I saw like some discussion about the hardware friendliness in like some blog posts that said that maybe it required more investigation. No, because I guess it's quite like I see that the fast Fourier transform needs a lot of memory access and all this, but there are other considerations that.
Yeah, so one thing that is interesting about it's essentially about the hardware friendliness of the sumcheck protocol, and one thing that is interesting there is that you need to, after each round of the sumcheck, you need to compute a Fiat-Shamir challenge. So you might have to send things back and forth from, say you do the sumcheck evaluation on a prover, then you might have to send things back and forth. a little bit more often, but I think there's two really important factors. Is that in the sum check, the size of the computation that you do reduces by a factor of 2 in each round. So it's really only like maybe the first 3 rounds that really matter, or that don't fit, or that are harder to fit into one machine, right? The question is always whether you can fit all of the memory into one machine or whether you can stream it. And it also turns out that you can actually do a transformation in the sum check where you increase the degree of the sum check. So you do a little bit more work, but it reduces the number of rounds. So you don't reduce by a factor of 2, but maybe you reduce by a factor of 4. And that, so then you ensure that even after one single round, you can fit everything into memory. So, there's definitely very interesting open questions still on how to do this, but fundamentally, the memory accesses of a sum check protocol are linear time versus an FFT or n log n. So fundamentally, I'm pretty convinced that, if you apply very smart engineering, smart tricks to it, it should be significantly more hardware friendly. But it's still, of course, we haven't implemented it, so our claims are a bit more speculative.
Okay, thanks. I think we need to move on to the next speaker. Okay, so next talk is Spartan and Bulletproofs are simulation extractable for free by Quang Dao and Paul Groups. And Quang will give the talk.
How do I present? How do I make this thing?
Oh, what?
Oh, cool. So, thanks for introducing me. So today I'm going to talk about my joint work with Paul Grubbs on our paper, Spartan and Bulletproofs are simulation extractable for free. So Spartan and Bulletproofs are examples of succinct non-interactive arguments, or ZK snarks. These are essentially non-interactive proofs that are also short, and for the purpose of this talk, I'm gonna consider Bulletproofs to be a snark, even though technically it doesn't have fast verification. ZK snarks need to satisfy first knowledge soundness and second zero knowledge. Knowledge soundness says that if the verifier of the proof system accepts, then the prover must have known some witness to the corresponding statement. And zero knowledge says that the proof hides the witness. ZK snarks have found lots of applications in blockchains, with lots of companies trying to build privacy and scalability primitives from ZK snarks. It's also found some other applications, such as proof of solvency, image provenance for combating disinformation, content moderation, and many more. Now, as ZK snarks are deployed in the real world, it turns out that in many situations, the standard security notions are not enough. In particular, we need to worry about two kinds of attacks. The first are adaptive attacks, where a malicious prover may choose the statement adaptively based on the proof. In this way, the malicious prover may be able to make the verifier accept a false statement. Secondly, we have malleability attacks, where a malicious prover may modify an existing proof into a new one without necessarily knowing the witness. These two properties are not ruled out by either non-adaptive knowledge soundness or by zero knowledge. And furthermore, there have been attacks on either adaptive for the Helios voting systems, or in the case of signatures rather than ZKPs, there have been malleability attacks against Bitcoin transactions. Thus, we need stronger security properties to deploy ZK snarks safely. One such strong security notion is simulation extractability, or SIMEX for short. Informally, it says that knowledge soundness still holds even when the malicious prover gets some extra power in the form of a proof simulation oracle. Here, the malicious prover may ask the oracle on any statement of its choice, even possibly false statements, and gets back simulated proofs. This is to mirror the power of adversaries in the real world, which may see a lot of proofs, for example, on a blockchain, before deciding to make a new one. Now, SimX rules out the prior two attacks that I mentioned, adaptive and malleability attacks. And it is also required to prove security for several private smart contract platforms. Prior works have shown that we can either construct SimX ZK snarks directly, or we can achieve SimX via generic transformations. Two more recent works have shown that certain ZK snarks are SimX out of the box and without needing any modifications. These include Sonic, Plunk, and Marlin, and also bulletproofs. These results, in the former case, apply to proof systems that are not transparent, meaning they need some trusted setup. And in the latter case, the SimX proof requires a stronger than necessary assumption, which is the algebraic group model. Thus, our motivating question is that, can we show transparent ZK snarks satisfy SimX under the same or the minimal assumptions used to prove soundness? Our results answer positively these questions. In particular, we show that for sparring and bulletproofs, which are two popular transparent ZK snarks, they satisfy SimX in the random oracle model, assuming the discrete log assumptions only. And these are also the minimal assumptions that is needed to prove soundness. For our results, we developed a few tools that we think might be of independent interest. The first is that we show how to instantiate a prior template for proving SimX from smaller properties. This is building on the work of Ganesh et al. Secondly, we show a more general tree extraction lemma for proving knowledge soundness. For the rest of the talk, I'm going to break it into two parts. First, I'm going to recall the templates for breaking SimX into smaller properties. Then I'm going to show our first main contribution, which is to instantiate this template for bulletproofs. For lack of time, I'm not going to cover sparring in this talk, although our techniques are similar. Thirdly, I'm going to talk about our generalized tree builder. So let's get started with the first part. Many ZK snarks and sparring and bulletproofs in particular are obtained via the Fiat-Shamir transform. It starts from an interactive and public coin argument and transforms it into a non-interactive argument by letting the challenges be derived from a random oracle. The main insight in the work of Ganesh et al. Is that you can reduce SimX of these Fiat-Shamir transform arguments into just knowledge soundness, assuming two smaller properties that I'm going to describe in a moment. These two properties are called K0 knowledge and K unique response. Let me first go into K0 knowledge. And to define that, let me first remind you what a normal ZK simulator can do. In particular, it may choose all the challenges first and then compute the prover's messages based on those challenges. In a KZK simulator, the simulator has a more restricted power. In particular, it may only choose the kth challenge first, and then it has to compute all the other messages in order, and has to query the verifier for the challenges in all the other rounds. So that's KZK. Now, for K-unique response, or KUR, it roughly says that a prover cannot produce two accepting proofs that agree up to round K. It may diverge from round K plus 1 onwards, but as long as, even if the malicious prover may choose the kth challenge and the statement, it cannot produce such two different proofs. Essentially, or in other words, that says that the proofs are computationally unique from round k plus 1 onwards. Given these two properties, the theorem is that SimX is reduced to a combination of knowledge soundness, KZK, and KUR. And this is for the same round K that we establish these two latter properties. Given this template, I'm going to show how we instantiate it for bulletproofs. And in particular, I'm going to instantiate it for bulletproofs range proof. Here, the relation is that we have a public commitment to a private value V, and we want to prove that this V lies in a certain range. The protocol itself consists of 3 rounds before it goes into an inner product argument. In the first round, the prover computes a bit decomposition of the value, sends the commitment to that, and also sends a commitment to some blinding vector. In the second round, the prover is going to send some commitments to some cross terms, and in the third round, it's going to send some evaluations at the challenge point X. So given this protocol, recall that from the template, we need to show that bulletproofs satisfy knowledge soundness, KZK, and KUR for the same round K. Let's focus on the latter two properties. So which round K should we choose in order to prove these properties? The heuristics that we use in this paper for Spartan and bulletproofs, and we think works more generally, is that we choose the last round where the honest prover requires randomness in its proof generation. In this case, it is the second round, since in the first 2 rounds, you can see that it sends commitments which requires randomness. And later on, it does not require any more randomness. So let's go into the proof of KZK for k equals 2. Recall that in this proof, we need to exhibit a simulator that may choose the challenge X first, but then has to choose all the other messages in order. This seems to present some problems, such as when we try to simulate this inner product argument. We cannot choose any of its challenges, and so it seems like the simulator has the same power as an honest prover. Indeed, this is unavoidable, and our simulator will execute the honest prover's algorithm on this inner product arguments based on some satisfying witnesses, L and R. To get these satisfying witnesses, it's going to run the overall protocol as an honest prover, but with a fake witness. Meaning, in the first round, it's going to compute some random A and random S, and then just try to execute the honest prover. At this point, an honest prover will not be able to complete the proof, but the simulator can. And this is because it has the power to choose the kth and the k plus 1th message at the same time. This is because we have already chosen the kth challenge first, and so we can choose the 2 messages at the same time later. Now let's try to go into more details. So let's pick challenge, and then we're going to pick some fake witness for the first round. Using these, I'm going to pick the third round evaluations randomly, and then set the second round commitments to be consistent with these evaluations. By consistent here, I mean to satisfy this evaluation check equation. Finally, since I had some A and S in the first round, I can compute some satisfying witnesses L and R for the IPA, and I'm just going to execute the honest prover's algorithm for this inner product argument. That concludes the proof of 2ZK, and now for 2UR, it says that a malicious prover cannot produce 2 different accepting proofs that agree on the first 2 rounds. It may choose the statement V and the challenge X arbitrarily, and yet it still cannot diverge from the third round onward. To prove this property, our main idea is that we try to simplify this protocol. And in particular, we try to first extract out the underlying witnesses L and R from the inner product argument. From this point onward, I'm just going to assume, without loss of generality, that the prover, the malicious prover, sends these witnesses along with the third round evaluations. Now, given all of this, we can split into cases, and then in each case, we're going to show that the malicious prover will break discrete log. I'll go into one case in detail. So if the first two evaluations are different, it turns out that if you look at this evaluation check equations, the middle term is determined once P star fixes V and X. No matter how it chooses V and X, once it fixes them, then the left term and the right term are going to be the same. And that leads to a non-trivial discrete log relations. The other two cases are handled somewhat similarly. So we have proven KZK and KUR for bulletproofs. The main ingredient left is the proof of knowledge soundness. And here I'm going to briefly go over our generalized tree builder. A common strategy for proving knowledge soundness is to prove a smaller property called special soundness. And to define the special soundness notion, I'm going to recall the setting of a Fiat-Shamir transform argument. From this malicious prover, we may define a tree of accepting transcripts, which says that the nodes of these trees are labeled with the prover's messages, and the edges are labeled with the verifier's challenges. It may split into K1 children at the first layer, K2, and so on to Kn. And every path from root to leaf of this tree forms an accepting transcript. Given this tree, special soundness says that there exists some K1 to Kn and a tree extractor that may extract a satisfying witness from any such tree. Given special soundness, the missing ingredient is that we need some sort of a tree builder that may interact and possibly rewind this malicious prover in order to get the tree that we want. This tree builder was given in the prior work of Atima et al. That builds any such tree in expected polytime. And thus we get special soundness implies knowledge soundness. However, we cannot apply this directly to sparring or bulletproofs because they don't satisfy special soundness as stated. Instead, they satisfy some generalized notion. In particular, first, the tree extraction. It may either output a witness or a break of some computational assumption. In this case, it is discrete log. And secondly, the tree of transcripts needs to satisfy some extra predicates on the challenges at certain levels in these proof systems. Our second contribution is to construct such a generalized tree builder that can handle these predicates for the case of bulletproofs and sparring. For the details for what these predicates are and how we construct this tree builder, we refer to the paper. So, in summary, we show that sparring and bulletproofs satisfy SIMX, which gives strong confidence that they will remain secure when deployed in practice. One limitation of our work is that since we use rewinding, our bounds for knowledge soundness are non-tight. This is in contrast to prior works, which use a stronger model, the algebraic group model, and was able to obtain tight knowledge soundness bounds, at least in the case of bulletproofs. I'm also going to end with some open questions, some of which have already had follow-up works. For example, this UC security paper was presented yesterday, and I also saw a recent preprint on this proving SIMX for more general classes of protocol. Thank you.
Thank you for your talk. Any questions from the audience? I have a question. No, there's some question. Okay.
It mightn't be it mightn't be needed for applications, but to the best of my knowledge, most applications of simulation extractability only need what is called true simulation extractability, where the oracle, is only on true statements, where you actually need to give a true statement and the witness. So I guess like two questions, like will anything simplify in your treatment if you do it? And two, do you actually agree with this statement? Do you really need for your applications full simulation extractability, or would true simulation extractability be enough?
Yeah, yes, thanks for the question. So true simulation extractability says that it only needs to hold for true statements, right?
The oracle, yeah, you can call the oracle only on true statements with witness. So you don't need, you don't give the attacker oracle on false statements. Yeah.
So yeah, I think I agree with you that this seems to be the power that adversaries actually have in practice. It doesn't seem to affect our proof or like doesn't simplify our proof anything, because like these simulators, when we construct them, they don't really care whether the statement is true or false. So yeah.
But at least for your applications, it is correct. I just want to make sure for your applications, you also need true simulation extractability. It's great that you get extra stuff, but for your, okay, cool.
Okay, then I would add to that. So no, well, it's not really. So what about this open question that you have of tighter rewinding proofs? Do you think there's any hope of this in this?
Yeah, so I guess like rewinding proofs usually, especially like in the non-interactive case, have a non-tight bounds. Maybe like one way is to somehow make our arguments tighter by maybe reducing the tree size by a little bit, or like reducing the factor of the dependence on the number of random oracle queries. But yeah, I don't see any path, at least like I don't see any idea to get it tight. Yeah.
Okay, thank you very much. I think it's time for coffee, so the session is over.
No, I think for small statements.